Going. Um, so a couple things that at the break we'll talk about. Um, we had a midterm, you remember. There will be more info about the exact solutions and what what we get back from the testing services. Of course, all your scores, but we also get exactly which bubbles you filled out. So I'll share that with you and an answer key and you know all the other information about that. So that's coming soon. What am I saying? Answer key and then plus your answers. Um, I'll share that with you electronically. Then you can look through it and decide if I robbed you of 3 points. And of course, any complaint you have will be totally fine. We'll just fix the problem. Throw our laptop to the ground angrily, or worse, throw our neighbor's laptop. It turns out. So in any case, we'll give you that information soon. I'll probably get to that in a couple days. I do have the answer key already, but that's how it got graded. Yeah, that was going to disappear there. So in any case, that'll be coming soon. So look for that, and then you can of course look through it and decide whether I came up with a reasonable answer key. And then we have projects coming up, so probably we'll release. Sorry, I'm working on it still right now. I wanted to release it yesterday, honestly, but we have a few more projects coming up. We certainly have a 4A and a 4B, which we have to squeeze in. This still relates to concurrency. We have to do a little bit more concurrency because it's so painful that you need to do it as much as you can, so it becomes somewhat less painful. It's usually when I announce that there's a rousing applause, like yes, more concurrency. So this class is a little different from that. And then what we'll do is we'll do one last little project, but we probably don't have time for a full 5A and 5B. So we'll just have one kind of project 5, which will relate to file systems in some way, shape, or form. So that's upcoming, which means it's going to be a very busy end of the school year. But just to make that a little bit easier, we're going to also have a final. So that's upcoming as well. That will be mostly focused on really just the last third of class, but we'll have a little bit on some of the other things because it's just kind of assumed that you know that stuff now. So we'll talk more about that in a few weeks. Until now, don't worry about that, but do look for these things coming very soon. Okay. So that's that. Any questions about that? Yeah. I think that you're not even allowed. You're not supposed to do that. It's a shame, isn't it? Yeah, I think it's just during the final. Yeah. Is that bad? Do people not like that? People like it? People don't care? Yeah. Oh yeah, the TA said the same exact thing. So, what I was thinking, actually, I'm probably going to release 4B first. It'll be here's the problem. What would be ideal is 4B, and then 4A, and then 5. Unfortunately, then you have to work till like the end of May. So what we're going to probably do is 4B, and then 4A, and then 5. Boo! Boo! All right. It sounds like people like that idea. That's what I'm hearing. Otherwise, you wouldn't get to do all these projects. Yeah, I'll be reasonable. It's not fully set yet. I'm trying to do some. I'm trying to be reasonable, but also make sure you do enough. So there's always, it's a balancing act. I won't be crazy one way, but how does the workload in here compare to other CS classes that are in the 500 or 600 levels? What do people think? Same, more, less? What? Easier than algorithm. Easier than algorithms. All right. So then I'm not worried at all. All right. That's because algorithms, you're just like, how do I prove this? And then you just look at it for a long time. Or you do what I used to do. It's like, here's my proof. You do like the first 4 steps, and then you're like, therefore, done. And then you realize that here's like the key insight is missing. This is where the key insight should go, but it's always missing. And then, like, I remember doing this. Like, the grader would be like, "I think you missed a step," and I'm like, "Yes, that's because I didn't know how to do the proof." So that's the difference, by the way, between like programming and proving things. Like you with the proof, you're still hoping like a human will like say, "Oh yeah, you almost got it," and in here, it's just like, "Yeah, that didn't work. You got a 0." So. So that's the difference. But I guess algorithms is harder, so we feel good about this workload isn't too bad. So yes, this will all be decided very soon. It will, be reasonable. It won't be crazy. We'll try to scope it properly. But I generally agree with your sentiment. It seems better to have kind of one thing do at a time, and that way you can just focus on that. And then if you get ahead of that, you can kind of start working on the next thing. So there's a little bit of flex that way. Okay, so more details on that coming very soon. Okay, so let's get back into this world of lecture and our high-level knowledge of how things work as opposed to writing C code or whatever. And so what we're going to talk about now, just in a little bit of detail, are hard drives, hard disk drives, or HDDs. We'll talk about them from a perspective of a few different things. We'll talk about the interface to hard drives, but mostly we'll focus on the internals. How does a hard drive work, and what is going on inside of it? It's amazing inside of these computer systems that we still use today, there are hard drives which are, have motors inside them, mechanical pieces that are spinning something around at thousands of RPM, and inside of there's all this chemical and electrical stuff that has to happen with these coated magnetic surfaces and all this craziness of how do you read bits off of a surface that's flying like that at such a high rate. All that stuff is, requires knowledge across such a huge spectrum of engineering and computer science. But what we're going to do is, of course, not focus on the chemical engineering aspect of it or the electrical engineering or any of those levels, mechanical engineering. What we're going to focus on is how a computer scientist should view a hard drive in terms of understanding its basics of its operation, and therefore how do we use the hard drive effectively inside of the operating system to get the highest performance or maybe best energy usage or whatever thing you want to optimize for from the perspective of of a programmer or a software systems developer. So that we're essentially building what you'll call like a model of a hard drive, right? It's an abstract model that reflects how the hard drive works without knowing exactly how do we coat a surface so that we can record magnetic material or bits inside of the magnetic material upon it. Okay, so let's look a little bit at internals of a hard drive again from kind of what I'll call a CS perspective on this of a hard drive. We think of the hard drive as having a controller of some kind. This is going to export the interface, which we'll talk about in a second, and then, like we said, control the operation of each request that's given to the device. The controller can be pretty sophisticated. It really is. In a modern hard drive, typically a little CPU in there running code that the people at, say, Seagate or whoever builds hard drives have written this code. A typical hard drive may have hundreds of thousands of lines of code running inside of it. It's actually quite frightening to think how many bugs are probably in the hard drive code. They're certainly not flaw-free. But yeah, all that code is just basically to control the operation of each request and make it work really efficiently. Then underneath the controller, which you can think of as the electronics piece, are the real, the kind of mechanics of the drive itself, where we'll talk about things like, the disk platters, and we'll talk about the ARM, and we'll talk about a bunch of other features like that. So just how does the hard drive work in general? And that'll be most of our focus. So let's talk first a little bit about this interface. Remember that a hard drive, what is a hard drive, right? A hard drive is, I guess we should just define that up here first. A hard drive is just a persistent storage device. And we say it's persistent, of course. We mean that when we turn power off to the thing, when we turn the power back on, the data will still be there. So it's a non-volatile device. This is in contrast with something like DRAM, where we constantly have to be powering it for the bits that we put in it to remain there. Once we turn off a system, give it no power, the DRAM, essentially, we can't rely on anything being in there anymore. And so if you just keep your data in DRAM, it's going to be lost. So if we think of our typical picture here with CPU and memory, and in this case, we have our, say, lone hard drive down here. Anything that's going on up here, registers in the CPU or memory, the DRAM that we have up here, when power goes off, all this stuff gets lost. So anything we care about, from the bits of a program we compiled to any data or a file that we have, anything that we care about has to live down here. And that's why we, of course, care about what we'll call this persistent device. We need some way to record information and not have to power the thing all the time. So that's what we're talking about. The interface to any sort of hard drive is actually very similar to the interface to memory. It's just a storage device. And so basically what you can do is you can read or write to it. Modern hard drives, or modern SSDs too, actually almost any modern storage device, have a very abstract interface. They just present themselves as a series of what we will call sectors, which are each, say, 512 bytes for various historic reasons. And each sector has a number, 0, an address essentially, through whatever, let's call it n-1. And when we want to access one of those sectors, we can issue, say, a read or write command. And the read or write command will specify, say, a sector, maybe a length, and then the write would be like a sector and a length, which is how many sectors, and then some data that goes along with that we wish to write to the device. The read would, of course, say, return some data, and maybe an error code, and then the write, of course, would probably just return an error code. Is that the entire interface to a hard drive? No, it's not. There are some other commands that you'll need to use in order to interact with a hard drive. We won't talk about those much today, but they relate to, just to give you a preview, for example, when you write to a hard drive, you really don't, that write isn't necessarily immediately written to the persistent part of the hard drive. It may sit in the device memory for some time, and so you might want to do something like make sure that that write has actually completed. There are some ways to do that via certain kinds of flushing commands. This will come up when we talk a little bit about journaling file systems in a few lectures from now. But for now, we'll just think we read and write, and we give an address, essentially, and that the sectors, as we call them, are 512 bytes. Okay, so any questions about that? That makes sense? Kind of simple interface. We'll just assume that interface. Okay, so now what we're going to do is we're going to talk about the internals of the hard drive in order to understand how it works. And then what we'll do is we're leading towards talking a little bit about I/O scheduling, which will be kind of the fun way we end the class, is by looking at like a little simulation of a scheduler and what types of things people do in device scheduling. So let's look at the internals first. The first thing we're going to start with is I'll draw a lot of circles in this part of the class, or try to draw circles. There's probably a better tool to do it. But what we have, our base hard drive has, is one or more what we'll call platters. A platter is just it's like something made of some aluminum, for example, some kind of hard metal. That's why it's called a hard disk drive. And it's just, you can kind of bang on one if you want. And I used to lug a hard drive to class. I had a hard drive from like a 1970s machine, but it's like this big and it weighs like 50 pounds. And class is too far away from my office. So if you want to see an old-fashioned hard drive, you can come to my office hours sometime. It'll be a very short and unsatisfying meeting, but you could do it. At the break, maybe, we'll take one more break maybe, and what we'll do at that point, we'll look at a video of an internal of a hard drive so you can see what one looks like. But in any case, there's just a platter, and it's coded on both sides, and you can record, it's magnetically coded so that you can encode bits, ones and zeros, into these sector-sized units onto its surface. And so that we have, like I said, we can have many platters. And they're rotating around kind of this, a spindle, this, what's called, so if I was drawing this from the side, so this is like a top view. But if we were thinking of this being a side view, you'd think of there being a spindle, and it's attached to some kind of motor, and it's spinning these like a platter. So this is one of those platters. And if you were doing this slightly 3D, you would like draw it like this. And then this is going to test the limits of my artistic skills, which are, you can see, limited. And this is, of course, going to give you a great idea of what this whole system looks like. But in any case, what you can see from this kindergarten view of a hard drive, when you ask a kindergartner to draw a hard drive, they'll probably draw something like this. But from the side, what you just have is a bunch of platters stacked on top of one another with some space in between them. And that space in between them, we'll talk about how much space is needed, but they're all attached to the same spindle, right? This is called a spindle, just like this thing that they're attached to that's spinning them all together at the same time, okay? So it's spinning, the motor is running, and the motor runs at a fixed rate, which we would think of as typical rates of how many rotations per minute are something like, say, 7,200 rotations per minute, or a fast one might be 10,000 rotations per minute, etc. So now we have a platter. We know it's magnetically coated. Somehow we can record bits onto that surface or read bits from that surface. We know we may have one or more platters, and that they're all spinning together at the same rate. But now what we need to be able to do is be able to put some information in some organized fashion down onto this platter, and then be able to read or write that data. So the way we're going to do that is we're going to organize the data into a bunch of concentric circles. We call each one of these circles a track. And then what we need to be able to do on a track is divide the track up into a bunch of these sectors that we were talking about. So each of these is a sector. And then what we need to do, of course, is to map the interface, which just looks like a linear array, down onto this particular, each of these tracks. So we might say, oh, this is sector 0, 1, 2, 3, whatever. And then let's say we got to 99 here or something. And then we might put sector 100 here, 101, etc. So somehow inside the device, the controller needs to know that mapping, right? The mapping of the interface down to which platter you're talking about, which surface of that platter, so they each have two sides, really, and then which track that particular data is upon as well, right? So we're mapping what is just a number to the user of the hard drive, like, oh, read sector 1000. It has to know exactly where that is in order to be able to read that. So that's tracks. Now we still haven't talked about how we actually read or write anything. Usually somewhere off to the side, there's something that is attached over here, and you can think of it as just being some sort of, another motor is attached to something that is called the arm. This is called the disk arm. And what this thing does is it can swing back and forth, and at the very tip of this thing is, let's just do that in red. What the red part is the read-write head. So here's the arm. It's attached here, and attached to it is this read-write head. And what the read-write head can do is, of course, either change the bits on the magnetic surface as they rotate under, or they can sense the bits, so they can read them as the bits rotate under the head. And the reason we have this ability to move this arm back and forth is because we need to be able to move from one track to the other in order to be able to read the specific data we're interested in. So if we're interested in, say, sector 0, the arm would move over here to this track because this is where that sector 0 is, and then maybe this would rotate under this way, let's say, underneath the head, and then we'd be able to read it. Then if we wanted to say, there's, let's say, an innermost track, and let's say there was sector 1000 on it, the arm would have to kind of rotate back over here and then be able to, or move back over here, and then have the specific, wait till the specific sector rotates under the head at that point. So just a lot of terminology, but hopefully not too complicated. What you're envisioning right here is just, there's a rotating surface. We have an arm on top of it. The arm has a read-write head attached to the tip of it, and it just can kind of scan back and forth. We call that seeking. We'll talk about more of that seeking in a second. And it can then go to a particular track, wait for a particular sector to rotate under the read-write head, and then go ahead and read or write it. Any questions about that generically? Yeah.
Does an arm responsible for the surface underneath it and the surface on top of it?
It's a good question. So we have, as we noticed in this expert diagram down here, there are multiple platters potentially in the hard drive. I'm going to redraw that and make it even simpler. We have this, again, this spindle which is rotating, and here's our motor which is spinning it at a fixed rate. And I'm just going to do it purely side view as if it's a perfect side view. So we have each of these platters. And then when we have, that means when we have an arm, it's really, when we have multiple platters, we don't have just one arm. What we really have is this kind of 3D thing here, which has an arm and a read-write head for each surface of each platter. But these are all attached together. So these are each independent these read-write heads all move together because the arm only has that 1 degree of flexibility. So it's kind of like, it looks like a kind of a fork scanning back and forth across these surfaces. And then we're only going to be accessing any one sector at a time. So even though we have multiple read-write heads, only one will be active generally for reading or writing of data at a time. So that happens all kind of, does that make sense how that looks? And we'll look at it again, maybe an example at the break. Other questions? Good question. Does it kind of make sense how that works? Okay, so let's go a little more detail then. So when we think about the kind of process of reading or writing, we essentially think of it as having 3 components. The first component is what we call a seek. This is the positioning of the read-write head over the correct track. Okay, so this arm here that we drew is going to be moving one way or the other to get to where we want to go. Of course, it's a physical device, right? Which means that when it starts, it accelerates, then it goes at its peak speed for a while, then it kind of puts on the brakes and slows down. And then it has to figure out it really is exactly where it is before it starts doing something, especially writing. Like you don't want it to kind of start writing early and then overwrite a bunch of nearby data. Tracks are packed very densely. You can certainly fit hundreds of tracks on the width of a human hair, right? So you have to be very precise in how you position the read-write head in order to actually do the operation correctly. And you notice here just how this works. These read-write heads are actually flying just above or just below, just a little tiny bit off of that surface, right? They're not actually touching the surface. They're just inducing a magnetic change or reading the magnetic change that's induced as the bits fly by. And so it's this crazy aerodynamic environment that's being created inside of here. It's just amazing that it actually works at all, especially at the rate that it works. But in any case, that's all happening during seeking. Now you might wonder, how does it seek to the correct track? Like how does it know where to seek to? Like how would it know I'm on the right track if there's so many packed together? What do you think is happening? Yeah. Yeah, right. That's the general right idea, which is that the hard drive is going to encode some information on the surface itself, which says, oh, this is track whatever, or these are sectors whatever. That's some sort of positioning information. Hard drives are constantly, as they seek across, they're constantly reading this information and making sure they're in the right position. Again, especially for writes. Like it's okay to start reading early, right? It's okay to start reading and say, hey, am I getting the right data? Once you're writing, you want to make sure you're 100% in the right place and then only induce the right when you're exactly there. So anyway, that's the seeking process. We get a large arm movement, a seek that takes some time. Then what we have is what we call the rotational delay, or the rotation, or the rotational delay. This is simply waiting for the desired sector to rotate under the head. And then the last phase here is called a transfer, which is where we actually do the read or write, whatever that is. So that's where we either read the bits off the surface, or we actually change the bits to what we want the new sector to be. Now, with a memory system, we didn't ever think about seeking or rotating. We just thought about transferring. We're storing bytes to memory, or we're reading bytes from memory. So it was all kind of all transfer. Here, we have a lot of overhead on top of the transfer, and we have to be cognizant of that overhead, because a poorly designed system will cause lots of overhead to exist, whereas a well-designed system will spend most of its time transferring. And let me just do a little example of that in order to kind of make that point. So again, we have seek, and then rotate, and then transfer. So let me write that down here: seek, rotate, transfer. So let's do a problem together. We can then think of the time for an I/O as being the time for a seek plus the time for a rotate plus the time for a transfer. And the real difference that occurs really depends how you treat the device. We think of a hard drive as being a random access device, which means we can kind of read or write any block of it. That's no problem. We can say read block 1000, then read block 1, then read block 1,000,000. But in some ways, it's not equally easy to access any blocks, because some blocks are far away from others, whereas others are close by, right? We know when things are far away, they're going to spend a long time seeking, right? The arm has to move a long way across the surface to get from a block, say, on an outer track to a block on the inner track. So that means if you treat the device in a certain way, it'll behave better than it behaves if you treat it in a different way. And so one way to think about that is like large I/Os versus small I/Os, and we'll see how that has a performance difference. So let me give it some example, and maybe you can figure out what's going on. So like the transfer of this particular hard drive, let's say that when you're doing the transfer, it happens at 100 megabytes per second. Okay, let's just say that that's true. Then let's say the average cost of a seek is, let's just make this up, something like 10 milliseconds. And then let's say the rotation average, we can kind of guess. When we arrive at a particular, when the arm has done its seeking and arrives at a particular track, how long will it take to, on average, seek to the correct track that's there, that it wants to find? Let's pretend, for example, that it's a 10K RPM drive, so 10,000 rotations per minute. That's kind of a faster rotating disk. 10,000 rotations per minute, if you do the math, like, dimensional analysis like you used to do in chemistry class, where you cross out a bunch of stuff and magically get an answer. If we want to turn that into how many milliseconds per rotation, that goes from 10K RPM to 6 milliseconds. So it's 6 milliseconds you do a full rotation. So then what's an average rotation going to take? Yeah, half of that, right? On average, when we get to a track, we'll have to wait half the rotation to get to the desired track. So let's say average rotation then, I'm going to make these numbers easier for you. I'm going to make this 7, and then we're going to make the average rotation 3 milliseconds. So then the question I'm going to have for you, let's say I'm doing 1 megabyte I/Os. Those are the large ones. So every time I do an I/O, I go to some location and either read or write 1 megabyte, versus I'm doing, say, 1 kilobyte I/Os. And your question then is, what's the performance of each of these? So why don't you use these numbers? Remember, I'm doing a seek, then I'm doing a rotation, then I have to transfer that data, however big that is, and then kind of compare the performance in terms of a rate of I/O of these two cases of I/O. So why don't we do that? Why don't you take 1 minute and try to just figure that out? And I will just stand here awkwardly. Okay, why don't we just do this together since then we can soon after take a break and really have a lot of fun. So, um, so when we think about this, what we're saying basically is the larger the I/O request you do, the basically the more time you spend transferring for that seek and rotation cost that you paid ahead of time, right? And that so the more time you spend transferring, essentially you're making that overhead of seeking and rotating go down, or what we might call amortizing that overhead. So let's say in the case of a large I/O, well, the seek takes, we said, 7 milliseconds. The rotation, we said, on average takes 3 milliseconds. So we know our overhead totally is 10 milliseconds. If we want to figure out how much time, what's our rate that we're getting out of our hard drive then, well, it depends on how much data that we're transferring. Now, when we're transferring 1 megabyte at 100 megabytes per second, how long is that going to take? Well, we have 1 megabyte, and we know that it's being transferred at 100 megabytes per second. This is like what I said is like high school chemistry. You just cross stuff out and magically you get the right answer. And here you see the answer is 1 over 100 seconds, or what we would say 10 milliseconds. Oh, we could even do more high school chemistry there by saying, well, 1 second is 1,000 milliseconds. And then we cross those things out, and boom, we cross those out, and we get the answer, right? 10 milliseconds. Doesn't that remind you of high school chemistry? That's honestly all I remember from high school chemistry is that you just do strings of these and you end up with the answer, however many atoms or moles or whatever. And it works very nicely here too. It's just called dimensional analysis. And basically what it tells you is it takes 10 milliseconds you'll spend transferring when you do for 1 megabyte. Now what's cool about that then is we know that we're spending 10 milliseconds seeking and rotating, and then we spend transfer time is another 10 milliseconds. And so if you think about that, just from a utility standpoint, like here's time, it means you're spending, this is all overhead, seek and rotate, and then this is transfer. And this is 10 milliseconds, and this is 10 milliseconds. And you can kind of see just by looking at that, that means that we're kind of getting 50% of our peak ability, right? It means that we're doing, and you can compute that as well. You could say you're doing 1 megabyte every 20 milliseconds, right? Which we know must be what? How many megabytes per second? We often talk about overall megabytes per second. Well, we can do dimensional analysis again. It's our old friend, 20 milliseconds, but you could just know by looking at it. What are we trying to get to per second? Cross those things out, you get 1,000 over 20, and you get 50 megabytes per second. And why does that make sense that we're getting that answer? It makes sense because we're getting 50% of our time is spent transferring. And if we're doing 50% of our time transferring and we have a disk that at peak could be 100 megabytes per second, it makes sense that you're getting about half that rate. Now, what kind of bandwidth are we getting? How are we spending our time when we're doing tiny little I/Os, kind of random I/Os all over the disk that are very little? Well, we still spend the same time in overhead, right? We still spend 10 milliseconds of overhead. But how much time do we spend transferring? Well, the answer is, well, you're only doing 1 kilobyte of transfer at 100 megabytes per second. So basically you spend very little time, 0 time. You could just say you don't spend any time transferring. It's actually very little. It's a small non-zero time, but it's approximately 0, which means that you're doing 1 kilobyte of I/O every 10 milliseconds. And again, you could convert that into a bandwidth. So let's go ahead and do that. 1,000 milliseconds per second. And you can see what you're getting here is 100, this cancels out, we get 100, we cross out one of those, kilobytes per second. Or maybe you could say, about 0.1 megabytes per second. So you can see the difference in performance by stark difference in performance, factors of 100 maybe, between doing little I/Os, kind of random I/Os all over the disk, versus when you move somewhere doing kind of a large sequential I/O, asking always for, say, a big sequence of blocks together. And so that's a general truism about hard drives, is when we're using them, we have to be very conscientious of how we use them. If we just scatter our data all over the hard drive, and access data randomly, we're going to get very poor performance. If we organize our data in such a way that we can always access the data in large runs or data that's near each other so we can kind of lower seek and rotational costs, we're going to do better. Yeah. Oh, that's a great question. So if we have our data, and for example, let's say it's on 2 tracks, so we like put it on this outer track, and then let's say it's spilled over onto, say, part of this inner track. You're 100% right that what would happen is when we're accessing this data, what would happen is you'd kind of scan the whole outer track first. It would go under, say, the head, and then what the head would have to do to get the next piece is it would have to move 1 track over. That does take a little bit of time, and so that will be a little bit of overhead, but we're going to organize the tracks in such a way that we don't feel a big cost there. But you're right, that's a little tiny seek in there, just kind of settling on the next hard drive over. But and that absolutely happens when you're going through, like, say, a few megabytes of data. You're going to jump across a few tracks, but it'll be done in such a way that you feel like a 1% overhead as opposed to like a full seek and rotation and so forth. Good question. Yeah.
Is there any limit to that? Like, generally, bigger is better?
Yeah, so certainly there are physical limits at some point that you can't issue an I/O that's bigger than some limit that the device or maybe the bus gives you. But you can still then issue, like, let's say I had so much work to do, I can issue a request for the first so many, I issue the next request for the next so many. It'll just the hard drive will figure it all out and kind of work on one piece after the other. But yeah, sure, eventually there's a limit, but it's not something that we would generally, it wouldn't affect our performance is what I'd say. Yeah, somewhere like an OS has to know about that, or whoever's issuing the request to the device. Other questions? So does the kind of flow make sense? We have a device, it has an arm on it, it kind of, the arm goes back and forth, we call that seeking. When we get to the right place, the right track, then when we just wait, that's called rotation. Then when we're there, when we finally get to the sector or set of sectors we're interested in, we go ahead and do some transferring, reading, and writing. There's a bunch more details there that we haven't talked about, but for now what we'll do is we'll take a next break, and then what we'll come back is kind of focus on some of those details by talking about disk scheduling, which is kind of a fun little sub-problem here. So let's take a little break.